Hello everyone, here's Jeder. Today I will introduce two ways to prove binomial theorem. First of all, I will prove the coefficient of binomial expansion is symmetric. So first, everyone must know that. So the sum of power of A and B is equal to the power of binomial, which is equal n. So for example, A plus B to the power of 3 is equal A cubed plus 3A squared B plus 3AB squared, then plus B to the power of 3. So you see, 3. 2 plus 1 equals 3. 1 plus 2 equals 3. 3 equals 3. So it's what I mean. And also we must know that all the combinations will appear at least one time. At least one time. Because right now we just assume we still don't know the coefficient. So yeah, so one time. So then, how to prove the coefficient is symmetric? I have an interesting way to prove it. So we just assume that A plus B to the power of n is equal K0 A to the power of n, then plus K1 A to the power of n minus 1 times B 1. So 0, it means the power of k. Then the third term will be this, K2 A to the power of n minus 2 times B here. Then we have many things between. Then we have Kn minus 2 A to the power of 2 to the power of 2. Then plus K minus 1 A times e to the power of 1. Then we plus Kn e to the power of n. So we just assume A plus B to the power of n equals this. And we still don't know the coefficient. But the next thing I want to do is I will change the position of A and B. So look. According to the formula here, we know that B plus A to the power of n should equal So according to the first equation, we can write the second equation. So we know that A plus B to the power of n is equal B plus A to the power of n. Therefore, it means it's always equal. So how can we make sure that it's always equal? Only if A to the power of n is A to the power of n. So only if K0 equal Kn. K1 equal Kn minus 1. K2 equal Kn minus 2. So on. Therefore, we can prove that the coefficient of binomial expansion is symmetric. So second part, we will directly prove the binomial theorem. So actually, a plus b to the power of n is the same as a plus b times a plus b times a plus b times a plus b. We have n amount of a plus b times together. So how can we get the coefficient? So I have a interesting way. So let's think about a plus b to the power of 3. So it's equal a plus b times a plus b times a plus b. Then let's see there. So for the first bracket, we can pick a or we can pick b. Then for second bracket, we can also pick a or b. Third bracket, same. Therefore, we can get a cube. So AAB is a squared b. ABA is a squared b. ABB is AB squared. BAA is a squared b. BAB is AB squared. BBA is AB squared. BBB is B cubed. So in total, we can see 1a cubed, a squared b, a squared b, a squared b, 3a squared b. Plus ab squared, ab squared, ab squared. Plus b cubed. So we did it. And actually, you guys can realize that. So if you want to get the coefficient of a squared b, it's same as a question that asks you the number of ways to arrange 2a and 1b on 3 position. So it's like that, 3 position, and we have 2a and 1b, so it can be AAB, ABA, then BAA, 3 ways. So we know that the coefficient of a squared b will be 3, like this. So how can we extend it to power of n? So if we want to get coefficient of the coefficient of a to the power of n minus r times b to the power of r, it's same as the number of ways to arrange n minus r amount of n and r amount of b on n positions. Therefore, we can use the formula. So the number of ways to arrange n minus r amount of a and r amount of b will be NCR. Yeah, if you know the permutation and combination, you can get almost, immediately get it according to this graph. So we just equal this. So that's why the coefficient, we can use NCR to calculate it, and also why NCR not only related to the coefficient, but also related to the combination and the permutation, something related. So it's really interesting, right? So for the last part, I will introduce a recursive way to prove the coefficient of binomial expansion, which is also related to a prime property of Pascal's triangle. So what can we do? So a plus b to the power of n is equal a plus b times a plus b to the power of n minus 1. So if we know the expansion of a plus b to the power of n minus 1, then we can know a plus b to the power of n by what way? So, for example, a plus b to the power of 4 is equal a plus b times a plus b to the power of 3. So we know a plus b to the power of 3 is equal 1 3 1. So yeah, is equal a plus b times a cubed. 3a squared b, 3ab squared plus b cubed. So I will show you how do I expand this bracket, break the bracket. So like that. Then this term, 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 this term. So it's like b then we can plus. So it's equal a to the power of 4 plus 4a to the power of 3 times b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. So how is this way to relate to Pascal triangle? Because look, so 1, 1, we know that the coefficient of first term and last term always 1, and 3 plus 1 actually is same as, okay, I will move it here. So 1, 3, 3, 1. So we know the first term is, last term is always 1. So 3 plus 1 actually is here. 3 plus 1 here. 3 plus 1. 3 plus 3. 3 plus 3. Then we get 6. Oh my god, here's no minus. And 1 plus 3. 3 plus 1 here. So, and there's 1. It's really bad. So, if we know the expansion of a plus b to the power of n, then according to this property, we can get the coefficient of a plus b to the power of n plus 1. So that's why it's called recursive way, because it's like if you know n factorial, then you only need time n plus 1 to n factorial, then you can calculate n plus 1 factorial. So recursive way is really important method in math, because it's like if you know a, then you know a plus 1, so you can use a recursive way to extend something to infinitive. So, okay, I finished. That's all the things I want to introduce today, and hope everyone likes my video, and please support me. Okay, I will upload more math video and more Chinese video. So please follow me. Good night.